So let's move on to part B. So in part B, we're given this so-called step function, which is equal to 1 when x is larger than 0, and it's equal to 0 when x is smaller than 0. So you can represent this graphically like this. So when x is smaller than 0 within this domain, the theta of x is equal to 0, and when x is larger than 0, it's going to be equal to 1. So this is what theta of x is going to look like. And then now we want to show that the derivative of theta of x is equal to the direct delta function. And this actually makes perfect sense because at this very point here, when x is equal to 0, you can see that the function jumps from 0 to 1. So you can imagine the derivative here being something similar to infinity at this very point, because it jumps from 0 to 1 within an infinitely small interval. And everywhere else, the derivative is just going to be equal to 0 because it's just a flat straight line. So that's exactly what the direct delta function is. It's equal to 0 everywhere else, and it's equal to infinity right at x is equal to 0. So this is what we're going to try to prove. And then in order to do this, as before, we're going to use this rule over here. So if we can prove that this is true, we can prove that d1 is equal to d2. So what that means is that we're going to try to prove that this integral will be equal to this integral. So f of x times the delta of x dx. And then we know that this integral is equal to f of 0. So if we can prove that this integral is equal to f of 0, then we would have established the fact that d theta dx is equal to delta of x, just as stated in this rule over here. So let's focus on this integral now. So we have an integral from negative infinity to infinity, f of x, d theta dx, and then we're going to use integration by parts. So we retain f of x, and then we're going to integrate d theta dx. So if you integrate a derivative, you just get back your theta of x. So this is evaluated from negative infinity to positive infinity. And then now I'm going to retain the theta of x, and then I'm going to differentiate f of x. So substituting in the bounds, we have f of infinity, and then theta of infinity is just equal to 1, because infinity lies within the region x is larger than 0, so theta of infinity is just equal to 1. And then theta of negative infinity is just equal to 0, because negative infinity lies within this region. So we can just ignore the second term because it's just 0. And then here I'm going to break this integral up into two parts. We're going to go from negative infinity to 0, so f prime of x dx, and then we're going to go from 0 to infinity. So you can see all I'm doing is that I'm breaking up the integral into two parts. So from negative infinity to 0, this is within the region x is smaller than 0. And then within this region, theta of x is just equal to 0. So this whole thing is just equal to 0. We can just ignore this. And then from 0 to infinity, 0 to infinity is within the region x is larger than 0. And then within this region, theta of x is equal to 1. So this term here is equal to 1. So now I can simplify this a bit further. So I can now take away the theta of x and replace it with a 1. And now we need to integrate this. So integrating f prime of x, you're integrating the derivative, you just get back the old function. And this is evaluated from 0 to infinity. So you have f of infinity minus f of infinity plus f of 0. So obviously these cancel out. So in the end we get f of 0. And so there we have it. Now we've proven that this integral is indeed equal to f of 0. So what that means is that this integral is equal to f of 0, which means that this integral is equal to the integral of f of x times delta of x. And this proves that d theta dx is indeed equal to delta of x, as stated by this rule over here.